All right, hello. Welcome to the early morning session. And we're happy to start Thibault Decoppet from Harvard CMSA to talk to us about what is that in symmetry protected 3+1 topological order.
Yes, thank you. Thank you very much, Constantine, for the introduction. Thank you very much to the organizers for the invitation. And thank you very much for all of you for waking up earlier than usual and braving the already noticeable heat. So yes, my talk today is going to be about symmetrics, orbital orders, and really from an algebraic perspective. But maybe so that we all have a common language. So I'm going to use Theo's probability definition of a topological order as a multi-fusion n category. Well, yes, but I mean, I guess if you put some like more mathematical substance on ideas of Lambda on the web, of course, in dimensions. Multi-fusion n category. Given the shaping this here, this is probably like, okay, well, let's go ahead and decide it. When? Apologies for that. The idea really is that, well, what is the topological order? What we know from Hahn one, certainly, is that the topological order be a field theory that is fully determined by algebra of attendant topological operators. And somehow the multi-fusion n category is an algebraic gadget that actually encodes, I guess the relations between. Sorry, thank you. Really, that was also. That's not true. Okay, and in fact. I will make a further simplifying assumption. So here in this definition of topological order, you are allowed to have degenerate bar states. And algebraically, so this corresponds to this condition of being multi-fusion. Okay, and so if you have trivial actually. Then you actually have a fusion and category. And in Aaron's talk yesterday, if you remember, so he had this assumption that the state space and the free sphere had to be one-dimensional. So this is exactly this solution, right? And in fact,
Sorry.
Yes, Constantine.
What's the difference? Fusion, multi-fusion?
So you all, yes, so you don't make this definition. This difference. So fusion means the monoidal unit is simple. Multi-fusion means the monoidal unit can decompose.
So if you have a matrix algebra over a vector, do you call that fusion or multi-fusion?
That would be multi.
But that's still a trivial DQFT, so.
So we don't want to.
Right?
I'm making the simplifying assumption that it has a trivial likelihood. An additional assumption to just simplify matters. But yes, I mean, I'm not saying these are not interesting more generally. I'm saying these are more difficult, probably to understand these very well before even trying to system. Okay. And under this condition, because topological order satisfy this notion of remote detectability, you actually expect a topological order with trivial vacuum to be determined by a braided fusion n-1 category, which would correspond to topological operators of codimension at least 2. And this is something. Can I attribute this to you, Theo? Are you happy if I attribute this to you? Joe, you don't agree? Okay. Okay, maybe I'll put Corbin when this is finished. there's an equivalence between, and I'm only going to write the algebraic statements, but there's some physical one, between fusion and factorial with trivial center. And braided fusion minus one factorial with trivial center. But to avoid that, we should say trivial center all the time and make form the latter of non-degenerate. That's it. And really, you should think of this non-degeneracy condition as analogous to the fact that the Mugger center of the modular tensor category is trivial. And it's really enforcing remote detectability. So you can think of it as a kind of higher S matrices being involved.
Doesn't work well when n equals 1, does it?
Was
Yeah. Fusion zero category trivial control from the complexity. Fusion zero category trivial center. Fusion one category trivial center, the other is
So what do you mean by trivial? Maybe that's where I'm having a problem connecting things.
well equivalent to vector.
Trivial at what state? The notion of equivalence, the center is like a one higher level of object. So
No, I mean the center is going to be like a braided fusion n category, and you ask this to be equivalent to n vector.
it would be good to keep track of floors. Sorry to complain, but trivial at different floors mean different things. That's why I'm getting lost. Morita trivial, braided Morita trivial, bit trivial, and like once you have so much structure, trivial as what?
as a braided fusion anchor. The unit equivalent.
Yeah, but this, like my complaint is that the center of a braided fusion n category is going to be fusion n category is a braided category already. So it's
Yes.
one, right? So
And I
it's
guess
trivial.
And trivial means that the unit inclusion for that braided fusion category is this.
Okay.
The unit inclusion for that braided fusion category is this.
Isomorphism as what?
As braided fusion. It is a braided fusion category. It's isomorphism.
All right.
Okay. And so in particular today, I'm going to be interested in kind of variations on the statement that topological orders in this one dimensions are classified by non-degenerate braided fusion 2 categories. So I'm not going to kind of definitely certainly not going to completely review the definition of a braided fusion category, a braided fusion 2 category, because that would take too long. But I'm going to give you some key features that are going to be relevant for my exposition. But personally, I always to attribute the definition of a fusion 2 category to Chris Douglas and David Carter. So, fusion 2 category. C is a finite and simple rigid colloidal 2 category with simple units. And really the key contribution is well, to make sense of what it means for a two category to be finite semi-simple, because somehow, rigidity and monoidality for two categories is all of things that people knew how to define 40, 50 years ago. And if you have a braided fusion category, well, maybe you can think of your braided fusion 2 category as being the algebra of codimension at least 2 operators in a 3+1D topological field theory. Right, so meaning that you have surface, line, and point defects, and in particular because you're in 3+1 dimensions, well, surfaces can braid. Right, this is why I have this adjective here. But in fact, we can also say something quite interesting about line defects. This is going to be my notation for the line defect. So this is So this is simply endomorphisms of the units in B. And because we're in 3+1 dimensions and I'm looking at line defects, this actually is going to be symmetric. And in fact, because this is a finite semi-simple, 2 category is going to be a symmetric fusion category. And here in 1 category. Yeah. Okay, so we're going to come back to this, but just before we come back to this, I do want to give you some examples. Again, for the sake of time, unfortunately, I'm going to be able to do too many examples, but there is a trivial example. So here, Constantine, 2 vector spaces, and as we all know, this is a 2 category of finite semi-simple 1 categories. This is the trivial thing. And once you have kind of replacement for your category of vector spaces, you can do usual constructions, and by the usual construction, I probably mean I can look at a representation of a finite group. In fact, more generally, you could look at representations of a finite 2 group. These will not directly come into the discussion today. And another important, another example that is really very important is, I guess, my notation, is this symmetric fusion 2 category of super 2 vector spaces. Really, so this is modules. Finite semi-simple module categories are symmetric fusion 1 category of super vector spaces. And many more than skip it. Fine. Now let's go back to this observation. So if you know your theory of tensor categories, or if you know your theory of symmetric tensor categories, you know that because we are working over the complex numbers, or really an algebraically still factors to 0, Damien proved that symmetric fusion 1 categories actually come in 2 flavors. So this symmetric fusion category is now going to be the category of representations of a finite group, where G are going to be a super version. So here the Z is a central element of the theory. I will call these supergroups. I believe Cameron used from Yoni groups today. And in this case, I'm going to refer to the theory as, I guess probably I should say as having all bosons. And in this case, I'm going to refer to the theory as having emergent fermion. So, hopefully I get to talk about the solution more at the end, but so this is, yes, you should really think of this C as essential element of order 2 as making emergent fermions appear. But that doesn't mean that your theory is actually genuinely fermionic. In fact, usually if you write a supergroup like this, you're not going to have a theory that's genuinely fermionic. All of these theories are bosonic, but some of them are perhaps more bosonic than others. Okay.
Say genuine fermionic? What exactly?
We'll come back to this in 20 minutes. Well, no, 15, maybe 6. Yes, a very good question. And I will answer later. And now we're going to do this. And now to build up some intuition towards the symmetry and risk topological orders. Really, what I want you to remember is kind of how you would approach this problem in 2+1 dimension. And in 2+1 dimensions, it's kind of well known that if you have a topological order, and you want to couple this to a zero form G symmetry, that means that you need to be able to introduce topological defects. And mathematically, what this means is that you must be able to build a so-called G cross-graded extension of your graded fusion category. And that's somehow exactly what we're going to do, but one at a little higher. So, well, dimensions with all ends and symmetry are. I mean, I'm going to write a lot of adjectives, mostly for experts. Well, this kind of G cross graded extension is kind of technical condition that you need, but don't worry about this too much. Extensions of non-degenerate graded fusion categories with. And really, again, so this piece of data is kind of your kind of original 3+1G topological order. You're trying to equip with a G symmetry, and all of these words, this G cross-graded extension is kind of the way that you actually implement this G symmetry. For those of you that have never seen G cross-graded object, I will not give a definition, but what you should know is that these data things have both a grading by the group T and have an action by the group T, and some other stuff. Those are the two that I'm going to come up. Yes.
standing the same as the group.
Yes. Yes. These two G's are all the same.
When you say I don't hook up, that means that this will be for G.
It's not the same as this G. As you'll see in a moment, I will have a picture that has a lot of groups and so on. Okay. And one thing that follows from kind of our exploration into this problem with Matthew Group is that we can actually give a kind of really concrete classification of these objects, which is not surprising because of course Long and Wen gave a very hands-on classification of these that was rediscovered by Theo. With bosons and the symmetry. So these are classified by, so you need another finite group, the tilde, projecting onto G. Projection. And you need a class, I think we're calling it phi probability. In H4, the tilde with coefficients in C star. And I should say that this is also related to more recent results of Hong, Lang, and Wen, where they obtain a similar classification in slightly different methods. Yes, you.
I'm still in the corollary on single bosons. So I understood correctly that in the definition, I could strike out with all bosons twice.
Yeah. Yes, absolutely. Okay. Okay, now it's 1. How do we actually prove this? Well, going back to ideas of common Wen,
But just to understand, what if G is trivial?
G is trivial. Yeah, so if G is trivial, we recover the well-known statement that these topological orders and supersonic all bosons are a choice of finite group and a class in H4.
What happened in the braid fusion category? Or...
Yeah, so it's like different. They're all Decoppet.
What is it classified by? That you can get with this category from this data, or it's actually structural.
Yeah, exactly. Well, I mean, there's a little bit of an yes, it's sharp to the obvious redundancy in the bottom.
So the groupoid of pairs of fixed G. So there's a groupoid there's a higher groupoid of topological orders, and there's one groupoid of G's what is subjective G's together with a high class gives the groupoid of multiplication. And I think we're saying that his higher groupoids.
Yes. Well, I only wrote down a pedestrian statement. Yes.
Clarify. Can I have like 2 different classes and geography that respond to the same grade?
If there's an automorphism of your group that exchanges them, but it's the only thing that can happen.
Okay. So I thought it like in one-dimensional lower could have different geographies. Oh, the same different variables. Like
no, this is correct. It doesn't happen here. Yes, it does happen on dimension lower. I'm happy to chat more about this afterwards. I think I can. I mean, here it's essentially like in one-dimensional lower, it's essentially because you kind of only have one level to play with. So somehow when you gauge things, they kind of stay in the same level. Whereas here, if you try to gauge things, you're kind of like going to go from like a 0 form to a 1 form symmetry. And so somehow you can never actually.
Never have classes with different
Not in this dimension.
Just, I'm going to repeat my complaints, condensing one. We haven't defined what we're talking about. Because as you increase the category level, there are different notions of equivalencies of objects. Like braid fusion categories form a 4 category, but there are many ways to say what the morphists are. I haven't told us. There are many ways to say what the isomorphists are. Right. There are different things. But just to understand the grounds of it, what dimension TQFTs are we talking about? And can you say in terms of TQFTs with boundary theories or defects? What's the structure? Because then it's clear. Then we know what's equivalent.
I mean, the
fusion categories could be equivalent as tensor categories, and Morita equivalent, braid fusion categories. You can get 3 layers of notion of equivalence, and so they're all different. So I mean, what equivalence means or classification means will differ depending on what you mean by equivalence. And you didn't tell us that. That's okay. Can you say it in terms of TQFT? And then maybe I can latch onto something.
I mean, I really mean braided monoidal equivalence. I'm building some braided monoidal, I'm building some braided fusion to categories.
Okay.
And I can, given this data, I can actually.
Wait, so 3 plus 1D, I forgot by now. Is the 4D theory you're talking about or 5D theory you're talking about? Or 3D, and what is this?
I think you should think of these as 4D theories with the 5-dimensional invert one.
4-dimensional, 5-dimensional vertical element?
Anomaly.
Anomaly.
They're allowed to have an
Anomalous 4D theory. Okay. With I presume some boundary condition, maybe even something like, okay. Actually, no, never mind. I can ask you later, sorry.
For the sake of time, I think I will do this.
Yeah, go ahead.
Which is important to do this advice, but anyway, well, okay, let me indulge myself, I will say something. So, the idea is actually quite nice because you have this gadget, so this is some kind of, well, this basically incorporated extension of a non-differentiated fusion boundary with portal. Anyway, lots of words. And if you follow this philosophy of how and when, really what you want to do is condense out all the lines, and then probably you get something that you can understand. And it turns out that this isn't exactly what we're going to do, but there's a little bit of a more roundabout way of doing it that is mathematically easier to actually implement. Because I don't want to have to think about what it means to, gauge all the lines in some G cross thing. That seems difficult. So instead, you rely on kind of a well-known correspondence between kind of a verified version of well-known correspondence between those degenerates. So it is categories containing again, I'm going to write it properly, but it's really an equivalence of at least groupoids if you set it up properly, even higher categories. And all these kind of things. Good. Remember. Right. British. With all those.
I'm going to ask you a question. What does this mean?
That's a good question. That's a probably forgot. Fully fixed.
fully fit.
I mean, you take loops and then you want fully fixed.
And it's central.
No. No. It's very much not. I mean, it's very much not central, right? Because it's from the generator, so it's like a room for it. But yes, I mean, somehow the key. I mean, the way you show this. The way you show this is a kind of abstract statement that you can get more or less for free if you believe in like fusion categories, and then you need to do some adjective matching. And very long list of adjectives on both sides. The point is on the generate here corresponds to, amongst other things, to faithfulness of the grading on the right. Yes, and somehow the fact that it contains 2G fully faithfully means that you actually get a fusion to category here and not something that has the moment.
It's not the point. It's not.
Yes.
It's not fully fit for it's not fully fit for once. Otherwise, that would be a stupid statement. It's simple. So you're only fully fit for once. I just wanted to say.
Okay, so we're going to use this. And somehow. The way you use this is if you have a P, well, like that. The P is what? With all of the affixes that are on this board. So what I can do is I can go like this way. So this is called, in terms of category land, we would call this the G equivalentization, but if you're like homotopy theory, it's just taking homotopy G fixed points. And the point is that now this is an honest to God graded fusion to category without this kind of like more technical things showing up. But it has this additional property that now it contains 2G. And if you unpack the little exchange we had with Theo, really you discover that what this means is that well, if I look at my line operators, this guy, this has to be representations of some finite group G tilde, and you discover that actually there must be a projection from G tilde onto G. And again, this is precisely corresponding to the statement that there's a fully faithful. But then you can do the more stupid thing where, well, now this guy will actually contain 2 rep of G tilde. So you can pronounce out all these lines. Well, I guess let's do some. And the point is that somehow we've done this back and forth, but somehow we've changed the group, so we've actually done something meaningful. And the point is that these are actually classifiable, so there are so these are just like G so far. Cross-graded. But they are actually extensions because we've kind of stopped all the lines, right? So this is something that Planck when observed. They're actually extensions of the trivial thing. They are actually extensions of 2 vectors. And it turns out that, as you might probably expect, cross-graded extensions of the trivial thing are actually the ones that you can understand. Well, again, it's a classical problem in tensor category theory. So basically, graded extensions of, let's say, well, I don't know how to write down the fractal A. Well, this right, right? Which is a braided diffusion two category. And these are classified by certain prominently classified maps. So by maps from B tilde onto B fancy pick A. And this fancy pick of A, so this is the space of invertible A module, like you just the space of invertible A module. The key point being, if you plug in A to be two vector spaces, well, this is actually a space that we understand very well. We try to Google it with a little bit of time. Turns out that it would actually be free of C star. And so if I plug in two back here I get B of B3 of C star. This is B4 of C star. And then if I trace it all the way back, I actually get the state direction. Yes.
Maybe I just missed this, but what if the relation of this to the classification of Ramshaw? Where I don't think they have those features.
Yeah, so they also more recently did have a version like this. But the relation with the work of Van Wen is, well, you can take G to be trivial, and then you actually recover the results.
Okay, so the G symmetry is, like you mean like a symmetrated ridge have a symmetry, like symmetry that not just
Yes. These are like GSCTs.
But the G tilde would be the
No, the G.
G tilde would be the like the category of photons.
Photons where?
Well, in there, like I mean, when you say like with all photons, I think that's referring to like you can consider the point light applications.
Yes, so I'm not allowing emergent fragments. I'm not allowing emergent fragments.
Right. And they form some like symmetric pattern, which is
Oh, you're asking me.
G tilde.
So we have to go back. So in B, it's actually going to be in B, it's actually going to be. So in B is going to be a graph of the kernel of this map. Yes, I know. Another question?
The reason why you did this differentiation is essentially the real
No, it stays. I gave up trying. I'm running out of time, so I did not quite hold this. I mean, sorry. Rather the point is that on the right hand side, like two vectors is not legitimate, right? So I don't actually need to tell you this. No, I mean the point of doing it like this in two ways is again because I don't want to have to like work with G cross-graded things directly, but it's too hard. So instead, classical mathematical yeah, it's more technical. Okay, so in the very minute amount of time I have left, I do want to talk a little bit about anomalies. So, well, I talked about these symmetry enriched topological orders, but usually what happens in practice is that you have like you start with a topological order that has a reaction. And then you ask whether you can actually realize this reaction by extending your topological order by including these defects that implement this reaction. For those of you that are more mathematically minded, what this means is that I might actually start with a braided fusion capacitor with a G action. And the question is there a, well, effectively braided G cross extension of B that actually realizes this action? Realizing. And in my negative time, let me very quickly tell you that if B is non-degenerate, there's actually a very nice fiber sequence that allows you to define an anomaly for the realization of this extension. So if B is degenerate, it is a fiber sequence that goes from B of this bigger space to B of the space of braided automorphisms of B. And then the interesting bit is that here on the left, we have this width spectrum showing up. And somehow, if you have an action, that means that you have a map to this space. And the anomaly is going to be the composite of this map, right? Because if this composite is trivializable, then you can lift here, which means that you can realize the action. Well, the option of my talk was supposed to be that you can actually do this in the genuine community and more to figure times. Thank you very much.
Questions or complaints?
If I understand correctly, this is all the story of the top level workers.
Yeah, okay.
Similar things were oriented.
I mean, probably there's so much to this. Maybe you should do this. Yes.
It's maybe it's a physical interpretation of this many chemical form. When we start with SP state, for example, SP state is T2 significant. Engage a subgroup of T2. And the T maybe is a portion of the T2. It's yes. Now that asking you a physical interpretation.
Yes. I mean, absolutely. I mean, this is closely related to your symmetry extension procedure. Yes. I unfortunately completely ran out of time, so I did not get to talk about it, but it's absolutely close.
Let's take Thibault again then. Five-minute break. I still have no idea what you are talking about. Are we talking about what field DQFT? Because for some kind of development, DQFT in PC. I know that the boundary theories are okay when I have what dimension are DQFT?
And then
3, 4, 5, like that.
that's what.
That's the full dimension I have, for example. What would be trivial for that? What happened to the whole notion of equivalence? That's
Okay, well,
the reason
I mean, that makes sense.
right.
Yeah, what's the-
Yeah, no, right. Yeah, yes, I think you know your number of things that have to
this is the point.
I do.
Five.
Right. Yeah. Well, okay, I get that. That's Interesting one. Yeah, or I mean, what I have to take with your paper. But you know, I just. All right, so I think before we go.
Yeah, I think it's time to start. Okay, so next we have Damien Calaque from Montpellier, who will tell us about a discrete 1D DQFT with a pointer.
Thank you very much. Sorry? Okay, thank you very much. First of all, a few disclaimer. I'm not a physicist, and so I might use some word I don't fully understand. Second one, there's no symmetries in my... Sorry? Okay, maybe. There are no symmetries in my talk, so sorry about that. And finally, like the physics content of what I'm going to talk about is like very light. I mean, it's only about like, in the end, it boils down to what's called topological quantum mechanics. But the talk is more about like working on a toy example that allows to see how homotopy theory can be used to understand some aspects of quantum field theory. All right, so yes.
So 1D means a space dimension or space-time dimension.
Time. It's just time.
I guess no space field dimension. Oh,
Yeah. So today I'll be talking about factorization algebra. So this notion has been introduced by Costello and William in order to model algebraic structure of observables in quantum field theory, and rather Euclidean quantum field theory. So let's start start with the definition. So factorization algebra on a topological space X, it consists of the following data. First of all, to every open subset, you assign a cochain complex. I'll be using cochain complexes, but actually you can work in any symmetric Mendel category. So that will be just an object associated to every open subset. Then for every inclusion of a finite set of pairwise disjoint open subset in a bigger open subset, you associate factorizing map, like, okay, what here? Well, I want this find it. And it has to satisfy a bunch of properties. So the first one is associativity, the second one is factorization, and the third one is gluing. When only associativity is satisfied, we talk about pre-factorization algebras. And let me now explain these three properties. So the first one, associativity, I'm not going to write it fully because like writing it is a bit of a mess with indices. But I'll take this example. And essentially what it says is that if you have a bunch of open subsets inside a bunch of bigger ones, and then a second step, going through the intermediate step or directly from the smallest open subset to the bigger one, it's just the same. So it's just a commuting diagram. Factorization just means that evaluating your factorization algebra on two disjoint open subsets boils down to just doing the tensor product of the evaluation on each of the ones. Well, and here by the same thing, I will always mean quasi-isomorphism. So if you have a good notion of equivalence in your category, I'd rather mean like the notion of equivalent than genuine isomorphisms. And finally, I want to explain so much about the gluing property for several reasons. So it's a local decouplable property. It can be written as a Cauchy property with respect to vice covers. So it's a kind of codescent condition. I will ignore it because in the case I'm interested in, which is the constructible case, it is automatically satisfied thanks to results of Carlson, Scheinbauer, and Walder. Okay, and what I will be mostly interested in here is observable for topological conjugate theories. So in this case, topological invariance tells me that essentially what happens on open subset of the same shape should be the same somehow. So the correct notion is the one of a locally constant factorization algebra here. So the property says that if an inclusion of open subsets is actually a homotopy equivalence, then the map between the corresponding observables is a quasi-isomorphism or your preferred notion of equivalence in your well-chosen category. So now the question is how much information or local information is needed to reconstruct such a locally constant factorization algebra. On flat space, there's an answer which is given by a result of Fleury. It says that locally constant factorization algebras on Rn are equivalent. So like here, I should use some word that people are scared with. So as an infinity category to En algebras, where En algebras are algebras about the little slope, right? So let me draw some picture to explain what let's say an E2 algebra is. So an E2 algebra is, let's say, some Cauchy complex. And for any configuration of disks in the unit disk, you would have an operation that goes from V to tensor the number of disks you have. So in this case, 4 V. And whenever you have a bunch of homotopies between such configurations, the corresponding operation should be homotopic to each other. In particular, there's some commutativity up to homotopic here because if you're looking at configuration of two disks, there's a clear homotopy that goes to the configuration when the two disks are in squares. Okay, so there's some commutativity up to homotopy. So somehow like this, I mean, if you think of like factorization algebra on Rn, using the factorization property, factorization algebra on Rn are completely determined by their value on connected open subsets. And the gluing property is actually telling you that on the basis of the topology, I should rather say factorizing basis, it's also completely determined by this. So basically on open disks. So a factorization algebra on Rn is completely determined by the value it has on open disks. So it looks very much like an algebra. The main difference is that for a factorization algebra on Rn, every open disk you associate a different vector space or co-chain complex. And the operations do not talk to each other, so there's no homotopy involved. So the theorem of Lurie is telling you that enforcing this local consistency condition somehow creates the homotopy between the maps that you have in an algebra. Maybe let me give you a bunch of examples for EN algebras. So E1 algebras in vector spaces with the usual tensor product, that's just associative algebras. Because of this commutativity up to homotopy and because for vector spaces, the only homotopies are just equalities. EN algebras for n greater or equal to 2 in vector spaces are, oops, there's a typo here. They are associative and commutative algebras. Sorry about that. E1 algebra in complexes are essentially the same as A infinity algebras. Essentially, you have your open intervals in the unit interval, and they can move a bit around, but you cannot swap them. So essentially, associativity is satisfied up to a bunch of coherent homotopies. To relate to things that we've heard about this week, E2 algebras in categories are exactly braided monadal categories. E3 algebras in two categories, I don't know how much people are familiar with this, are called selective monadal categories. So that's as close as it can be to symmetric, but not exactly. So, and essentially, whenever you have like an EN algebra, if you're in a higher category, if the category does not have enough room for higher homotopies, it's going to be fully commutative. There are a bunch of weird examples I want to talk about. So in complexes or vector spaces, with the direct sum as tensor product, as monadal product, every object is canonically an EN algebra for every n. It's just because every object is a commutative monoid for the plus operation. Though, if you change a bit this category and talk about the category of vector spaces or complex with a pairing, this is not true, just because the pairing is not a map that preserves the, because the sum is not a map that preserves the pairing. Essentially, when you pair two things which are in the sum, you have cross terms, and this says that the pairing is not preserved under the plus operation. I'll come back to this point later. So what I've been working on with Victor Carmona is a kind of like finite scale version of Lurie's theorem. And essentially, what the main idea is to say that, I mean, if you have a locally constant factorization algebra or like a topological quantum field theory, and you look at those observable at a certain scale, somehow topological invariance is telling you that the size of your open subset does not matter so much. So you should be able to reconstruct what happened at small scale, so for small open subsets, from the data of what happened at open subsets which are big enough. So here's the setup. We fix a positive real number that we call the scale, and we're looking at the following thing. So we're looking at locally constant prefactorization algebra, so the same game as before, except that we restrict ourselves to open disks of radius strictly bigger than this fixed scale R. And the result just says that it doesn't change anything. So those things are still equivalent to in algebra. So somehow, if you're giving yourself this locally constant prefactorization algebra on disk of size greater than R, you can reconstruct what happens on small disks using local constancy. So maybe two observations here. The first one is that even though it sounds very similar to these results, the strategy of proof that we used cannot be implemented here. The main reason is that in Lewis proof, you're using that the configuration of disk in the unit disk, that's homotopy equivalent to configuration space of points. And so there's he uses a version of the Seifert-Van theorem, and you need for this your configuration of disk to be a cover of the configuration space of points. And if your disks are too big, this does not work. So there's a bit of like a rescaling implementation to perform here to go around this problem. Now, how can we use this? For concrete models of topological point field theory. The idea is the following. So pick your favorite topological field theory, consider a lattice approximation of it, then compute it, compute the observable on big enough open subset. Why big enough open subset? Because if you take too small one, like let's say you might actually miss any side of your lattice approximation, and it's going to be just like trivial. So essentially, usually the scale R here depends on the mesh of the lattice, and then you get an EN algebra, and that's going to be the EN algebra that encodes the structure of observables of your topological field theory. All right, so let's see an example. Let's see how it works in dimension 1. So, yes.
That's the particularly using the right speaker to get the same.
Yeah.
That happens. What happens when you get
Yeah. So, the algebra of observables will be quasi-isomorphic. So adding these sites won't change the. Exactly. So we will see it on a concrete example, like in one or two slides. So let's see what happens in dimension 1. So we have a locally constant, I should say, prefactorization algebra on. We call this not too little d, so not too little involved in there. So it's valued on intervals of radius at least r, so like size at least 2r. Well, no, yeah, there's a discrepancy here. So the consequence, as we have said before, we have we know that it gives an E1 algebra in complexes. So in this case, that's an A infinity algebra. So it says that the value of our factorization algebra on any big enough open interval is going to be equipped with an A infinity algebra structure. And up to homotopy, this A infinity algebra structure does not depend on the choice of the interval AB as soon as B minus A is big enough. Okay? And if we want to compute, let's say, the algebra structure on the cohomology of this, it's very easy to compute. So we basically take three numbers. So A, B, and C. So C is squeezed in between A and B. We assume that the size of those three intervals are big enough. And basically what we do is we say that the inclusion of AC in AB and CB in AB gives rise to quasi-isomorphism. So I can invert them up to homotopy. So in cohomology, that gives an isomorphism. And then I use the factorization products. And that defines for me the product on cohomology. If you want to express the A infinity structure, you can use a bit of the same game to keep track of the higher homotopy. But at least if we're only interested in what happens in cohomology, that's how we can do it. And essentially, in the next example I'm going to give, the cohomology is concentrated in degree 0. So the complex is quasi-isomorphic to its cohomology. So there's no higher homotopies. So here's the model I'm going to use. So let's start with a vector space with a skew-symmetric pairing on it. It doesn't need to be non-degenerate. So essentially, that means like, let's say that V is finite dimensional. That's just a constant Poisson structure on the dual of V. And for every interval, I'll be describing the linear observable, so the complex that is dual to fields. So it's a two-term complex. So in degree -1, we have functions on Z with values in V. So we have like a bunch of sites, and at every site, we should associate a vector. And we put a support condition that this function is supported on the interval A, B -1. That's what we have in degree -1. And in degree 0, we have exactly the same thing, but the support condition is just that it should be supported on the interval A, B. Right? So it's going to be 0 outside this. And the differential is just the discrete Dirac differential. So like the value of the differential of f at n is just the difference of the value at two nearby sites. Sorry. So that's why I said like these are functions defined on Z with a support condition. So they are defined on the whole of that, just that their value is 0 outside of. So these are, I mean, the continuum analog of this would be like homologous Fourier functions with support inside the interval. And the support condition is made so that the differential is indeed well defined. And then there's an.
-1 by the outside is supported in the benefits. And then it's H plus 1, like a little bit more than that.
Sorry?
Because when the sum of that of n, when n is just slightly more than a, then n -1 is slightly less than x. Wait. It comes out, never mind. I'm just confusing myself. Let's take back all concept.
If you have like a delta function at n,
Yeah.
it's just delta n plus 1 minus delta n. So it works pretty well. Any function is a linear combination of those things times the vector.
What's it? Like,
so now if the support is between A and B -1, n should be in between A and B -1. So yeah. Also, I got confused several times with this. So. All right, and then there's a degree +1 pairing that's defined on these observables. I mean, the choice of the formula doesn't matter so much. It's just that it's a derived bracket. So, and the claim is that you can check that it's compatible with Q. So Q is really like compatible with the pairing, and so and the assignment that to an interval associate these linear observables is a prefactorization algebra for the direct sum, and that's where having disjoint things matter, because if you look at the sum operation for things that overlap, the map is still defined, but it won't be compatible with the products, and it's only going to be compatible with the pairing. Sorry, when things have disjoint support. And then you can run this. I don't know what name to give to it. So it's probably familiar to people who are used to BV quantization. I'm following a scheme that appears in Owen Williams thesis for it's a quantism scheme for free theories, and they call it BD quantization with Kevin Costello. It's just a matter of convention how you pack the additional BD operator, but that's essentially the same thing. Okay, so we start with a complex as before with a differential Q and this degree +1 pairing. And essentially, classical observables are going to be defined as the symmetric algebra generated by the linear observables. And we extend the definition of Q to the symmetric algebra by the Leibniz rule, and the same for the pairing, it extends to a degree plus 1 brackets. So the observable form an odd Poisson differential graded algebra, or many people call this a P0 algebra. Nowadays, that's to construct the quantum observables, we can see that if we shift our complex, so instead of having it in degree -1 and 0, we put it in degree 0 and 1, and we had a central parameter h bar that sits in degree 1. These things can be equipped with a Lie algebra. Essentially, the bracket between u and v is going to be a multiple of the central parameter h, and this multiple is given by the odd bracket that we have, or the odd pairing, and the parameter h is central. And essentially, the quantum observables are the Schrödinger complex, the complex of Schrödinger chains on this Lie algebra. So that boils down as a vector space, or as a chain complex, to be sim of w bracket h. So we just add this parameter to the h to the classical observables. But now the differential is deformed, and so it's the old differential plus h bar times something. And this something, if you're not used to this Schrödinger thing, it is an order 2 operator. That is the operator that people call the BV Laplacian, and it's completely determined by the odd pair, the odd brackets. And the point is that this assignment that W associates Schrödinger of G of W, it's functorial, it's exact, so it's a quasi-isomorphism to quasi-isomorphisms, and it is symmetric monoidal. So it preserves free factorization algebras, and it sends locally constant things to locally constant things because it sends quasi-isomorphism to quasi-isomorphism. So we were having a locally constant prefactorization algebra on R, well, on not too little disks. And now we're having a locally constant prefactorization algebra with values in complexes, but now with a tensor product. So if we're back to our example, so we had this linear observables. We can compute the cohomology of this. So it was given by a two-term complex. If the interval AB contains at least one site, so let's say if AB is has length at least 1, then its cohomology is concentrated in degree 0, and it's just the original vector space V we started it with. So essentially, the quasi-isomorphism is given by sending V to this complex. What was this? Like this linear observables. We send a vector to vector times the data function at this site, and this sitting in degree 0. Okay, and this is a quasi-isomorphism. I'm not saying anything more than the round cohomology is concentrated in degree 0 and is given by constant function, except that we're taking completely support things, so it's kind of a dual statement. Okay, you can view it in another way. You have a kind of integration map that takes the sum of all values of the part which is in degree 0, and that's also quasi-isomorphism. Okay, so essentially the cohomology is always the same as soon as the interval is big enough. So we have something which is locally constant, and we apply the quantization scheme given by this Schrödinger complex. And so we get a locally constant factorization algebra on the real line, which is locally constant for intervals which are big enough. And so, as we said before, this defines an algebra structure on the cohomology. And it just turns out that's not a surprise, that it's the Weil algebra. So that's the simple calculation. And so the Weil algebra is just like the tensor algebra modeled out by the relation that the commutation of U and V is given by H bar times the pairing of U and V. Probably calling it the Weil algebra is a bit improper here because I haven't assumed that the bracket is non-degenerate, the pairing is non-degenerate, but we can still define this algebra. Okay, so when did I start? Okay, so like 3-4 minutes left. Okay. So there's a version of this theorem with defects or with boundaries this theorem that we proved with Victor Carmona. I'm not going to explain this in full generality. I'm just going to explain it in like dimension 1. So now you take the real line and you assume that there's point defects. And so there are 3 types of intervals: the one which are at the left of the defects, the one which are at the right, and the ones which contain the defects. And we're gonna, for those ones which contain the point defect, we're gonna assume that they are symmetric. So there are interval of like the type -a. And so now we are gonna define prefactorization algebra on open subset of that type. And we are going to enforce the local constantness condition if and only if an inclusion of interval inclusion of interval of the same type. Okay, so that's instead of local constantness, I'd rather call about constructible condition here. And so the theorem is essentially the same. If you have a locally constructible prefactorization algebra for this type of open intervals, the result says that this data is the same as the data of 2 E1 algebra and a bimodule between them. Okay. So let me mention that this constructible factorization algebra on flat space, they've been introduced. I mean, they've been used by Claudia Schambauer to construct the higher Morita category of EN algebras, and I can't refrain to, because we've seen this picture in several talks. In general, a constructible factorization algebra on that stratified space, that's a 2 morphism in the higher Morita category, so that these are like 2 E2 algebras, they are objects. They have E1 modules between them, and these E1 modules have shared a bimodule in between. All right, so okay, so now what I'm going to do rather quickly, I'm gonna have a vector space, and now I'm gonna have an isotropic subspace, which means that it's contained in the kernel of the restriction of the pairing to it. So the pairing vanishes on this subspace U, which means that the pairing descends on the orthogonal of U modeled by U. And essentially, that's going to be our reduced space. So this has a Poisson geometric interpretation where we dualize everything. So this star has a constant Poisson structure. The subspace of linear form that vanishes on U is quasitropic. And this U circle mod U, this is just the dual of the reduced vector, I mean, of the reduced vector space that we get. And for this, there's also like a well-known consideration. We can take the Val algebra of V, and we can take the left ideal generated by U. It is acted on from the right by the normalizer of this ideal modeled by the ideal. And there's one thing that when you improve is that this normalizer of G mod G, that's the same as the Val algebra of U circle mod U. So essentially, we have 2 vector space with pairing. That there's V and there's U circle mod U. We take the Val algebra of these 2 things, and there's a natural bimodule between them, which is defined in a purely algebraic way. And the game was to try to recover this with a discrete model where we have a point defect. And the game is the same as before. So for open interval that do not contain the defect, that's exactly the same definition as we had before. But for the left side, we use V, and for the right side, we use U circle mod U. And for intervals that contain the defect, we have to say something. And so instead of the definition, let me write a picture. So we have our sites. Let me do this with interval -2, -1, 0, +1. plus 2. So that's the sites that we have. And we also have the homological degree. So if we have in degree minus, okay, so we have degree -1 and degree 0. So we're going to have V, here. That's U naught. Oh, no, 0. Okay. So that's how it works. So functions in degree 0 on the non-positive sides, they should take value in V, and on positive side, they should take value in this other vector space U naught minus mod U. And for the function in degree -1, V for negative sides, U naught for 0, and U naught mod U for the positive ones. And the differential that I wrote before comes down to saying that we take alternating sum of those maps that goes straight up or in the diagonal way. Okay? And now, actually, that's actually a way to prove local constantness. You can see that here we have an identity. So that factor is acyclic here. So we can kill it. And the leftmost factor that goes in diagonal is an identity. We can kill it as well. So we recover the same thing. So this was observable for the interval -2 plus 2. And now we're back to the observable for the interval -1 plus 1. So that's actually that proves local constantness. There's still one acyclic factor here. And we are left with U0 going to V plus U0 mod U. This map is injective, so it doesn't have any cohomology in degree -1. And the cohomology in degree of 0 is just the quotients by U0. So we have V plus U0 mod U. It means that we identify any vector in V with a representative of something that is in U0 mod U. So the cohomology in degree 0, that is just V mod U. Okay? And when you apply sim to this, sim of V mod U, that's the sim of V, which are the observable for, the theory that is on the left. And that's modeled out by the ideal generated by U, which is exactly what we're interested in. And so like a bunch of calculation shows that when we compute the bimodule, we indeed get the two value algebra acting on this bimodule. Okay, so like that's all for today. What we aim at doing now is incorporate, of course, interaction. So we'd like to test this with an L-infinity algebra, and in particular, where this L-infinity algebra comes from a geometric origin, we would recover feathers of deformation computation of constant rank Poisson manifolds. We have an ongoing project for like doing this on the circle, but now two big intervals, you cannot have access to them. It's not so useful on the circle, so we have to go back to some kind of renormalization where you have a compatible system of factorization algebra for discretization, which are finer and finer. And we have actually a way to, we've worked this out in the case of 2D Yang-Mills with Giovanni Felder, where we recover the within computation of the partition function. Okay, sorry to be over time. Thank you very much.
Questions?
Yeah.
So you expect to balance and you have to update show that it's still or is there something general that says like, oh, you told by
So
the remaining conversation.
So yeah, the point is that for free theories, this was an example of a free theory. You just like everything comes from the structure of linear observables. So you have your linear observables, and the quantization is a functor that goes from like linear observables, so like vector space with a pairing, to complexes. So it's a functor and it preserves quasi-isomorphism. So it preserves the property of being locally constant. Whenever you have interaction, that's going to be a bit more complicated, but I guess at least if you do something perturbative, it is fine because you'll use a deformation theoretic arguments.
Yeah, so the thing it reminds me of is in three-dimensional quantum field theory, honest quantum field theory, there's a theory of super selection sectors. You get those by taking a time slice in R2, and now take very large disk, and you get an E2 category.
Yes.
So this looks like it should be able to fit in your scheme in some way.
Yes, it does. There's a work of Victor Carmona with Benini and Schenkel, where they do exactly what you suggest. So yeah, the answer is like it's very similar. So like they have to adapt a bit the situation, but it works like in a very similar fashion. Yes.
Yeah, hold on. So you said that for group, Victor does not use that.
Sorry?
The group, so like Bruce group relies on some string cases. You can do that. So your group does not rely on cyber.
Oh, we use Seifert compound, but for different space. So like we can not directly adapt the proof, but at some point we use Seifert compound. Yeah. The proof boils down to proving that some map of infinity operator is a localization, and yeah. So the whole strategy of proof is actually quite different. We can talk about this, but it's not a weak approximation. Well, it is in Lewis proof, and it cannot be a weak approximation.
Let's take Damien again. Take another 5-minute break. Yeah, I'm Adrien. Good. Okay. Yes. And that what? Yes. And the whole yes. 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 And you can unmute when they say start. Yes. Yeah. There is just now it's muted. Okay. I think it's a sketchy, but here does not. Kind of. Oh. That's a oh yeah. Yeah, we go first. Yes. Yeah, yeah, so 5 for this. 4 minutes. There are 5 minutes break as we do, so
we have to be. And the coffee bread is after mine, so that's the issue. That's okay, it's probably very. I know. Here, I mean, oh, okay. Yeah, no, not in Paris. I mean,
Paris.
so you asking which university?
Yeah, well, maybe it doesn't matter.
Paris Cité.
Oh, it's maybe just Paris. Right?
Yeah. Nobody understands.
Okay. Okay. Our next speaker is Adrien Brochier from Paris. We'll talk about Swiss cheese, Poisson group, and topology.
Hey, will you talk? Okay. Okay, so thank you for the introduction and the opening to speak here. So I will talk about some kind of TFT perspective on the theory of Poisson groups. So let me start with a quick definition. So for the purpose of this talk, a Poisson group will be an affine algebraic group, which I will assume to be finite dimensional and connected. Together with a Poisson structure that is multiplicative in the sense that the multiplication of the group is a more Poisson variety, essentially. And quantization of a Poisson group is a quantization of the underlying Poisson variety, which is also a deformation of the Hopf algebra of function on the group. So somehow you want to deform the Poisson structure while keeping some kind of compatibility with the multiplication. So in the perfect world, you would like to keep the same product. It doesn't work in general. So we have to deform. But there's still this old theorem that says that you can always so I should start right away by saying that everything I'm going to talk about depends on something called a Drinfeld associator. You don't need to know what it is. It's just some highly complicated, very non-canonical choice that you have to make at some point. And then everything will sort of depend on that black box. And so this theorem from the 90s by of Kashdan and Damien is that not only quantization of Poisson groups actually exists, but there's actually a functorial quantization of those, which is in sharp contrast with, I don't know, Kontsevich deformation quantization of ordinary Poisson manifolds. Of course, many people here know that there is equal formality behind this. So what I want to do in this talk is first I want to review some sort of, I want to say folkloric TFT interpretation of that section. And by folkloric, I mean, I don't think it's written exactly that way in the literature, but a lot of people, including in this room, have thought about this. And basically what I want to emphasize is that there's a lot more to this story than just the sort of mere existence of this constitution. So again, it's not new in any sense of the term, but I want to sort of emphasize this. And then I want to illustrate this by considering the seemingly trivial case where the Poisson structure is actually 0. So it's, I believe, related to BF theory in physics. And it turns out that even in that case, where the sort of quantization problem turns out to be trivial, there is still a lot of interesting structure which is around, and you get a lot of interesting stuff from that. So let's start. So sort of basic result about this Poisson structure is that they're encoded by some structure on the Lie algebra. Basically, because they're multiplicative, we can sort of put back everything to the origin. And they are in one-to-one correspondence with so-called Lie bialgebra on the Lie algebra of G. So this means that you get a Lie co-bracket, which satisfies some axioms, dual of those of the algebra, plus some compatibility condition. And the nice thing about this notion of Lie bialgebra, just like for ordinary bialgebras, is that it's actually self-dual. So if you take the dual vector space and then transpose the map, and there's this slightly annoying thing that you need a minus sign here, which is not very important, then this thing is also Lie bialgebra. So it makes sense to pick some Poisson group with Lie bialgebra G, and call this a dual Poisson group of G. And then another important ingredient of that story sort of merge those together. This is a so-called Drinfeld double of G, which happens to be also the Drinfeld double of G dual. This is kind of important. And the idea, you take the vector space of G and G dual, and you can check that there is a unique Lie algebra structure on that space, which satisfies the following two conditions. So first of all, G and G dual are Lie algebras. And then the sort of obvious pairing on that space is D invariant. So basically, it's telling you that if you have finite dimensional Lie bialgebra, there is a standard way to construct the so-called matrix of Lie algebra. So Lie algebra with an invariant non-degenerate pairing. And this is basically where the TFT will come from. So now I pick a group D with Lie algebra D. And even if that's not true in general, just pretend that D is G plus G dual as a variety. It just makes things simpler. So the sort of first part of the bulk of the TFT we want to consider is you can look at character varieties for D. So you look at the moduli space, or really I should say the moduli stack of representation of fundamental groups of compact oriented surfaces into D. Or you can think of this as moduli space of flat bundle on D. And the claim that this non-degenerate pairing on the Lie algebra gives you a canonical Poisson structure on that moduli space or moduli stack. And you should think of this as a generalization of the perhaps more familiar Poisson structure on character varieties with value in reductive groups. So there is, to a large extent, one of the motivation for this theory is that reductive groups, they are almost Grunfeld-level, and somehow this is kind of a generalization of that. And you should think of this as some version of the AKA seed Poisson sigma model, where you're looking at maps from your surfaces to the classifying stack, which is a quotient of a point by your group. And one of the important features of this, it's actually a TFT, first of all, so there is a natural compatibility with gluing of surfaces. And this is where you really need like the stacky version. It wouldn't be true for the ordinary varieties, but it actually satisfies something slightly stronger than that. It's compatible with smooth embedding of surfaces. And this turned out to be quite important. So now you can consider, so this was somehow like the classical TFT, which will produce some geometric objects out of the surface. And then you can linearize by taking category of vector bundle or maybe quasi-coherent sheaves on those objects. And in particular, and again, this is where it's important to work with a stacky version, to the disk, you will attach the category of representation of the group. And from that perspective, the objects of that category you can think of as point defect for the series. So you can have surfaces with marked point, and the marked points are labeled by representation of G. And there's this, I guess, familiar picture for many of you that the tensor product is given by collapsing points and the symmetry of braiding by sort of moving points around. So all this defines the bulk of the series. And then G and G dual defines for you left and right boundary conditions. So if you add this into the mix, you can mark interval or circle on the boundary, either in red for VG or in blue for VG dual. And again, you get some stack with some Poisson structure. And all of this is again compatible with gluing on things like that. So higher algebraic perspective, which again many of you are familiar with. So that this version is due to Safronov, and it uses formalism of shifted Poisson structure due to Calaque, Antef, Tovenvaki, and Vegecy, which the thing that is pairing on V gives you a two-shifted symplectic structure on BD, and BG and BG dual are two-shifted Lagrangian in there. And the sort of key assumption that makes everything I'm going to talk about works, even if we can go around this in general, is that those boundary conditions are transverse. So now if I look at a square with one red interval and one blue interval, so this is the same as taking D and modding out by G dual on one side and G on the other side, so there is nothing left. So this is just a point. And remember that this TFT is compatible with embedding of manifolds. And in particular, one important feature is that it's compatible with embedding of the empty manifold. So each of these objects has a canonical map from the empty manifold. And the claim that in that case, this is actually an isomorphism. So we get a nice commutative diagram like this, where all the maps are embeddings. And I should emphasize that the compatibility of with respect to embeddings tells you that all of those have a monoidal structure, which you should think of as being obtained by like stacking thing on top of the other. And all of those maps are compatible with that in sort of an obvious way. So when you apply your TFT on this, you actually get a diagram of monoidal functors. And the claim is that in that classical case, those monoidal functors are really just restriction or forgetful maps. So D and G dual are a subgroup of D, so you can just restrict along the subgroup, and then you can just forget your vector space. So those are those maps, and this is obviously a commutative diagram, like in sort of very strict sense in that case. So in that case, we get something that's maybe a little bit boring, but the idea is that this sort of picture can be quantized fairly easily, or easily, maybe stronger, after you choose an associator. So once you've made a choice, everything has a canonical quantization. So the very first object that you produce out of it is a braided monoidal category, or more precisely, a balanced braided monoidal category, or framed E2 algebra, if that's more of your liking. And the sort of crucial property here is that you're not changing the underlying category. So you're taking the same category, and you're just deforming the braided structure. And again, if you don't know what a Grunfeld associator is, basically that's what it does. That's basically everything you should know about this. So that's how you define the sort of the quantization of the bulk of your series. And then if you want to quantize the boundary condition, you need a little trick, which is basically you want to work internally to this category. So basically you want to work over BD. And the way you do that is, well, that's kind of a nice thing working with stacks, that the thing that we want to be true is actually true. You can just take the quotient of B by, of a point by G, and multiply top and bottom by B, and you get the thing on the right. And that's where this duality shows up. So basically the quotient of the point by G is the same as the quotient of G dual by D. And so this dual group arrives. And so here's this category of representation of G, which is O of G comodules, is actually the same as O of G dual modules, but in D. And the tensor product here, which is the tensor product of vector space, goes to the tensor product of over this commutative algebra. So if you're familiar with this, you can think of this as some discrete version of causal duality. Like there is no causal duality in vector spaces, but if you're working internally to categories, there's somehow enough room to make something like that next. Another nice thing is that you're not talking about the Hopf algebra in Vex, but about the commutative algebra. So in particular, an E2 algebra inside some E2 category. And the nice thing is that now you can apply your construction again. Sorry. And it turns out that this commutative algebra, equipped with the same product, it becomes a braided commutative, aka E2 algebra in your braided monoidal category. Say again?
That could have been. This is a surprise thing.
What do you mean? That you don't have to change the product?
Yes.
Yeah, it's surprising. It really works because we're working with these three categories. But I mean, it would work in general. So there is this. So basically, associators gives you a way to construct E2 algebras out of P2 algebras. So we have the P2 category and the P2 algebra in it. And even if we are working in a GD setting, associator will give you a quantization of that. It just so happened that here there is no room for the E2 structure to be more complicated than that. Or rather, but I will say that here being an E2 algebra, that would be a condition, not extra structure. Maybe that's one way to think about it. Anyway, so you get this braided commutative algebra in A, which means that it's commutative up to the action of the braiding. And basically, the sort of thing you want to be true is true, meaning that modules of such a thing is a monoidal category. And it's actually better than that. It's what's called a Swiss cheese algebra, which means that if you take this category of module, you will get monoidal category B. And then you can take this Greenfeld center, which again, I think many of you are familiar with. This is basically a way to produce a braided monoidal category out of monoidal one. It's a categorification of the center, and then you have a braided monoidal map from A to the center, maybe with some opposite here. So you should think of this as a categorification of the notion of algebra over commutative algebra. You can think of an algebra over commutative algebra as a map from your commutative algebra to the center of your algebra. So that's the categorification of that. Anyway, so long story short, whatever the technical details are, the important thing is that this is exactly the kind of algebraic input you need to define a two-dimensional TFT with two colored boundary conditions. So the way you do that is to use the formalism of either factorization homology, as in Daniel's talk, or perhaps more familiar to some of you, the notion of scaling categories. So you again get a TFT that attach categories, or rather pointed categories, to surfaces maybe with some marking. Again, you get some boundary condition, and again, I claim that they are transverse in the sense that so this is what you would attach to a square with a blue and a red interval. And again, this is monoidal by stacking vertically. And the unit is actually a monoidal equivalence. So I already said that. And just like before, you can apply this TFT to the diagram that we have, and you get a diagram of monoidal functor, which again is commutative, although in a very highly non-trivial way this time. So once you have this diagram, in particular here, you get, so B here is a deformation of rub G, and you get a monoidal functor from that category to vect. And then there is some abstract so-called Calaque formalism that tells you that if you have a monoidal category and a nice monoidal functor to vect, then you can construct a half-hash bar out of it. So somehow if you only care about, and I claim this is a quantization of G. So if you only care about that, somehow all of this was just to construct this map. Basically. This was the thing that was sort of hard to construct. And the claim that one way to construct this map from B to vect is actually to construct this sort of thing, and then use this boundary condition as transverse to get something into vect. But of course, we get much more than that, and there's like kind of the symmetry in this diagram that we sort of want to use somewhere. So basically, I claim that even if you the quantization of this in not everything, you have a lot more structure than that. Basically, what I would say. So to spell it out a little bit more precisely, what I mean by there is a symmetry between G and G dual. As we saw on the previous slide, we also got a quantization of G dual somehow for free. So the idea, if you take a thing of Calaque formalism and you apply it to get a quantization of G, you get a quantization of G dual as a byproduct. But no, G dual itself is a Poisson group. So you could just apply a formalism to him directly, and you get a quantization of G as a byproduct. And the claim is that those are pairwise isomorphic, but in a highly non-trivial way. So the sort of TFT perspective tells you that they have to be isomorphic, but because everything is up to homotopy or isomorphism of functor, this isomorphism is still highly non-trivial. So at the end of the day, you get some kind of compatibility condition with so-called duality on double, which was understood by Enriquez on beyond entity of Kaplan functor. But somehow this TFT perspective made all of the symmetry really sort of manifest. And at the end of the day, so remember that this category, rub 5D, is undeformed as a category. We just change the monoidal structure, bread monoidal structure. On the claim that this composition is still the forgetful functor. And at the end of the day, what we get is a highly non-trivial monoidal structure on that. And in turn, this monoidal structure is given by the action of some element in the enveloping algebra of D. And the claim that somehow this is the sort of star of the story. Like all of this structure, the switch to structure, the both of the quantization, somehow they're all encoded with very complicated elements. And I claim that even if all of this is sort of abstract nonsense, at the end of the day, you can write an explicit formula for J, by which I mean explicit internal phi, which is very not explicit. In fact, not only you can write on the formula, there is actually a universal formula, which is given by some kind of linear formal possibility of acyclic Feynman diagram. And somehow this is where the fact that this quantization is functorial comes from. You can do this at the universal level. And for sort of later use, I want to emphasize that once you have these elements, the product on this algebra is sort of quite easy to write on. This is just act with J and then applies with visual multiplication. So the formula for the core product is more complicated, but I will only need the product for that. So any questions so far? I should have asked that before. Okay, so this was sort of a crash course on the TFT perspective of editing of Calaque. So let me try to give some kind of application of this. So take any finite dimensional affine algebraic group and put a zero structure on that. So in that case, the quantization problem is actually trivial. So first of all, let me tell you what the dual group is. This is just G dual with the Poisson structure coming from the bracket of G, seen as an abelian group. And here KKS is Kirillov Constantin. So the claim is that this is actually not entirely obvious, but this is true. So if you apply this Decoppet quantization to those, well, for G you would get nothing. There is nothing to do. And for G dual, you get the enveloping algebra of G. So of course, it's well known that the enveloping algebra of G is a quantization of the Poisson manifold G dual. I claim that as a half algebra, it's kind of trivial, but I want to emphasize this is a quantization of the Poisson group G dual on first. And the trick is that the fact that this is a flat deformation comes from the PW isomorphism, which is the vector space isomorphism to the symmetric algebra. And the claim is that it's actually a co-algebra isomorphism as well, which is why you really get a constitution of a Poisson group. And let me recall one of my favorite terms by Flo that says that the order S of G is commutative algebra, U of G is very non-commutative. When you restrict to invariant, you can actually find another isomorphism between those. So part of that statement is the fact that this algebra is actually a commutative algebra, which is true. And you might think that just restricting the PDW isomorphism is sufficient, but it doesn't. You need to twist by some very complicated differential operators. So this is a very deep and very hard and very important theorem in complete analysis on representative theory. And the sort of popular interpretation of that theorem is that when you need U of G, G invariant is commutative because it's the center of U of G. And likewise, this is the Poisson center of S of G. And I should mention that this is the on quantization should commute with taking center. So that's kind of philosophy. And there are precise version of this. In fact, there is a derived version of that result, where really you should think of this as a quantization of what's on the left-hand side. So this is sort of the common way to think about this. Yeah.
So, left side of your right is going to be entirely what depends on the real necessity.
Here you mean?
Well,
I mean,
after we're upstairs, if you want
yeah,
to
but
take interpretation.
so that's my point. It is sort of trivial case where it looks at the zero structure. Like the output was not quantified.
Sure. Here I see, I'm asking about this interpretation of the geometry of the problems. Are you, do you see the real necessity?
No, not yet.
Oh,
Yeah. Yeah, I mean, so well, if you go to the derived version of that, then you start saying as zero.
Adrien,
Formality, yeah.
I think you see some information of phi. It's the gamma function of the S.
Yeah, right. Yeah, that's true. Yeah, so somehow you will become only get on fire. Like there is, I mean, not for actual Liège. Like for Liège, by vector space, you will always be the same. But if you want to thinking about universal thing, there is like an action of GRT on the space of equal functions. And sort of, that's okay. Anyway, so that's kind of one sort of common way to just think about it. But somehow we kind of miss part of the structure. Here you're just thinking of G rho as a Poisson manifold, but not Poisson group. It would be nice to have somehow this divide somewhere. Sort of another motivation to switch to a different perspective is the proof in 2006 by Alexei Torsion of the Cauchy-Riemann conjecture, which was a sort of far-reaching generalization of the Flo theorem formulated in 1976. So that's not the first proof of that conjecture, but the first proof found only 2 years before by Alexei and Meyerken. And it's kind of surprising because the proof uses associator, and when you look at the paper, it's really like a lot of things looks like they should have something to do with setting of Catalans. But the proof is really very, very algebraic. You just see the same equation, but somehow in a different space. So basically, in a way, I wanted to understand that. So a different way of thinking about this, the different isomorphism is to go into the realm of Poisson group. So in that case, the Drinfeld double is just the semi-direct product of G individual with respect to the action. And the claim is the same. So this is basically spec of S of G invariant, or rather this is a stacky version of that. And the claim is that you can think of this as this double quotient, which is just the image of the square with two intervals. So the claim is that when you think about Poisson groups, this space we try to understand sort of shows up naturally, and in fact there is a version of that for average rate Poisson. And again, this thing will be a monoidal category by stacking vertically. And so if you're taking global section, which in that case is homomorphism of the unit, you will get a commutative algebra. So that's where that's one way to think about the commutativity of the thing that we're looking at right now. On the sort of fancier version of that, it's this is actually an intersection of two Lagrangian and something two-shifted symplectic. So that has to be one-shifted symplectic, which wants to quantize to a monoidal category, and in particular, it's Poisson commutative in degree 0. Anyway, so a theorem that might look a bit weird right now. So the claim is that these elements that encode everything, this acts on any pair of objects, on the tensor product of any pair of objects in graph G. And the claim is that if I restrict to G invariant on each factor, then this guy will act trivially on this. Okay, so that's a fact. And first of all, I want to emphasize this immediately implies nuclear theorem. Well, at least if you also know that theorem. So if V and W are S of G, if they act trivially on this, as I told you, the multiplication is given by acting and then take all the usual multiplication. So it means that on G invariant, the multiplication is isomorphic to the undeformed one. So on one hand, it sort of immediately implies difference theorem. And with really lots and lots and lots of insights, I claim that this is actually the Cauchy-Arban conjecture. So this might not be surprising to you if you don't know what it is, but if you look at the original Cauchy-Arban conjecture, it looks more and more complicated than that. There is some Lie formal series and some complicated sort of divergence equation, but 40 years later, you can sort of reformulate it in a slightly simpler way. And the proof is really sort of obvious in that perspective. So the first part is that just from looking at pictures, this statement should be immediate if we're looking at dual invariant instead. And so, symmetries. The last step is to use this duality property. And again, the fact that this duality symmetry really involves some highly non-trivial isomorphism is related to the fact that the Duflo isomorphism is non-trivial. So in that case, this sort of symmetry, this is where this Duflo element comes from. And the fact this is not just the PVW isomorphism, but something more complicated is sort of hidden there. Okay, so I'm almost done. 5 minutes on coffee. So just to finish on some topological perspective on this. So in this story, along the way, we get two actions of the bread group on the algebra function on G in the end. So the first one is we can think of this as an object in the Drinfeld center of work. So because the quantization was trivial in that case, the monoidal category we get is just G from Ettinger formalism, formalism. So we can take Drinfeld center, so we get an action of the bread group on that. You can check it's really just really easy to see that this is the same as the action that comes from taking of the bread group as the mapping class group of punctured disk with n punctures, and G to the n as a representation right here of that. So the free group, the fundamental group of disk with n punctures, the free group of n generators. And so if you choose where you map each of the generators, the space of representation into D is D to the n. So this carries an action of the bread. And you can just check explicitly that this is the same one as seeing O of G as an object, the Drinfeld sum. So it's kind of surprising because this is really straightforward, and I feel it should be well known, but I don't know a reference for that. People seem to be surprised that this is the case.
This is or this is not the action of vectors and permutations.
Say again?
This is or this is not the action of vectors and the permutations.
No, it's not. It's not just permutation. No, it's well less trivial than that. It maps. It basically like sigma I, the generator that exchange I and I. One it maps one of the is permute one of the generator and send the other one to the conjugate. This is like the specialization of the RC representation, which is phase 2. So it's definitely good. Okay. So it comes from if you take a loop on the puncture disk, see the lemma on the free loop, and then you sort of start moving points around. You just this is not just permitting. So this action is definitely not trivial. And then there is another action that comes from seeing O of G as an object in this category that you construct from Drinfeld associator. And I claim that this one has something to do with the isomonodromy action on flat G connection, again on the puncture disk. On the claim, so I brought this as a theorem as well my own, but it's really like somehow in that case, we don't need to construct the quantization. We already know what it is. So I think of Kaftan, rather than tell you, hey, this quantization exists, it tells you that actually such a map exists. So in that case, the sort of interesting part of HQ of Kaftan is the fact that there is a blend money that took off from this thing that becomes an oscillator to this thing that doesn't. And the claim is that it's kind of easy to see that it's map of G to of G. So you get it intertwines actions. So one way to think about it is as some sort of combinatorial version of the fact that the Riemann-Hilbert correspondent is compatible with mapping class with actions. But for me, the reason I wanted to think about this is because there are this really cool paper by Alexei Henriquez Storsil and Barnett and Blanco, where they sort of observed that this Cauchy-Arvin conjecture has some surprising connection with this action of the bread group. Well, basically, I wanted to understand why. Okay, thank you for your question.
Question.
Maybe we can see different mapping class convention.
Not yet. Yeah, I mean, that's really a natural question. I think there is something special in the zero, which I can't explain not now, but I can explain. And I would like this, especially since there's also sort of like Alexei, I was meeting on my head on the so-called Goldman for where they have some relation between this Cauchy-Arvin conjecture on like characteristics of arbitrary group services. So there's definitely something like that. But I think yeah, the hurdle is not just more complicated, there's something that's slightly different. Second, sorry. Oh, I mean, yeah. I know like maybe three things about stacks. On one of them is this, hopefully. That if you have a subgroup, when you look at the intersection of PD and BG, you're inside PD, that will be sorry. Is that correct?
Maybe just one check.
Again?
Maybe checks on the right name.
Oh, yeah, sorry.
This is a quantity, yes.
Again? Yeah, sorry, but you were also asking about this. This is also true, that's not quite right.
And can your boundary condition can be treated as like effects?
Sorry?
Can your two boundary conditions, at least in the case where you have G and capital G and little G, can those be treated as a near effect versus Neumann boundary conditions?
I don't know.
I understand this by as the
So I can't hear anything, sorry.
I understand this red P with subscript 5
Yes.
as Greenfield yet to over this L phrase number.
So this will actually be necessary.
It's red. This is
Yes, yeah, I mean, well, it's in the final marginal case, the rotation of the actual will be able to move it. Interesting about the room is like that no question.
Yes, it's pretty good.
And at the end, here, from the 5D to,
So the Drinfeld center of the,
right, that's not equivalence.
that, I guess that's similar to the previous question. That's close to being equivalence.
Okay, so
So yeah, the right hand side would be yet a Greenfield module for O of G, I guess. And I'm not entirely sure about the co-module version. So there's like some finiteness issue, but they're almost the same.
I have one question.
Well, nice. I mean, in that case, they might be exactly the same actually. It's close to being equivalence anyway, in general.
Okay, let's take Adrien again. Let's take. Yes. Yes.